Okay. The chart is copied.
Okay. You can... you can, like, scroll down, I guess.
Yeah. Here we go. Hold on. I got you right here. You can check your email one more time.
What's up?
You can check your emails one more time.
Okay.
The new 2 small papers. So you don't have to like rely on me scrolling and stuff like that
Okay.
all the time. And then I can make some more space here for myself.
Got it.
You got them?
Yeah.
Okay.
Okay. Use the following to help you create a viable procedure. Okay. Sorry, I have to change the brightness of my monitor because I have like so much light coming in from behind me. Okay, so let's see. Watch the following video from the stock room on Blackboard. Okay, observations of cations. Number 2, the set is separated into 3 different data tables. Provides a list of observations noted while performing experiments on known cations. Okay. Okay, data table below. Alright, we put that in. Okay, use the following to help you determine what your unknown is. Unknown 1, unknown 2, unknown 3. So are you like assigned one of these unknowns?
Number 6.
What's that?
Number 6.
Got it. Okay. So you have unknown 6, and so when you add ammonia, you get a clear, colorless liquid on top, rust-colored precipitate on the bottom. So okay, we don't really know. Well, rust-colored is kind of like orange precipitate, so it might be iron, but let's see if when you add the NaOH, the precipitate did not dissolve. So that's likely iron yet again. And then when you add HCl, the milky, cloudy precipitate came back after HCl was added. So, milky cloudy precipitate. Well, okay, that seems like... Okay, this seems like that your unknown is a combination of perhaps aluminum and so the unknowns, like they're did you send me that other document where it explains what you do in the lab?
Oh, okay. Right now you can look at my screen while I send it to you.
All right, let me open that thing again. Okay. Oh, okay. So, all right, let's see. Unknown. Yeah, go up. Okay, so let's see. We're going to be, working with these 4, okay. No 2 ions, okay. All right. Okay. All right, you can go down to the next page.
Okay.
Okay.
I just sent it to you.
Okay. All right, I think I got it. So basically what we're doing is we're adding a chemical. So first we're doing the separation step.
Mm-hmm.
So what we have when we add NH3 is we have a clear colorless liquid on top, right? Which is going to basically be it's probably going to be like the aluminum. Wait. And then rust colored on the bottom. So the precipitate forms on the bottom. and we put it in a centrifuge. And when it does that, it basically causes that precipitate to, be stuck on the bottom of the test tubes.
Okay.
That is called the centrifugate. And then you wash it with water and recentrifuging it. And that's just to, I guess, separate it. So when you add the ammonia first, some, hydroxide might form, okay. The color could be in some kind of identification process or procedure. Let's see. And then after that, so you have unknown 6. So when ammonia was added, so for copper, I suppose you can write well, okay. It says clear colorless liquid, so I mean, are you supposed to write? I'm trying to figure out how to. Like for data, is that what you write? What should happen, or what does? Okay, so.
Oh no! For data, that's literally just like what we've collected. So that like little chart that we were talking about with the NH3 added and whatever.
Yeah.
That would be included in data, and then I guess some results. We would include what unknown we think we found, whatever it is.
Mm-hmm.
Like what it's asking over here. Read. State which unknown you analyzed and whatever, and then yeah, we can just literally like put that. We can put the results we obtain, how you use the results, and yeah. So literally, we just put like whatever results we get over here, and then the rest of it that it's asking at the bottom here is what goes in the discussion.
Okay. Results of your analysis are just state which okay. Oh, okay. We do the unknown after we do the test on the known solutions. Got it. So okay, so for this, oh yeah, I need to request edit access.
Oh really? I had it for everyone to edit. Hold on. There you go. I updated it.
Okay.
You can edit now.
Okay, so when ammonia was added, we can say for copper, let's see, color changed from light blue to deep dark blue with no precipitate. Okay. For cobalt, color changed from light pink to a deep yellowish to a deep yellow with no precipitate. Oops. And for aluminum, color changed from clear to a cloudy. Wait. Okay. Oh no, so the color did not change. Color remained clear. However, a cloudy white gel-like precipitate formed. Then for iron, color changed from yellow to a dark orange. So okay, color remained yellow. However, a dark orange fluffy orange again. Wait. So, okay, sorry. That means that the color did change. Okay, so color changed from yellow to dark orange, and a fluffy orange precipitate formed. Okay. Now, when we add sodium hydroxide, what up? Yeah.
No, I said when we add the NaOH.
Mm-hmm. So, okay, I guess for some reason they say no addition of NaOH for copper.
Because there was no precipitate formed, so for copper and cobalt, we would just put none, not available.
They added 5 drops for cobalt. So, okay.
Sodium hydroxide.
Oh, I see. Oh, you're saying only, okay, got it. Only if a precipitate was formed. So not applicable. And then for cobalt.
Applicable.
Wait, only if when a precipitate was. Okay.
Yeah, so only for aluminum and iron.
Okay. Okay, so this is when
applicable for the next section too.
So the So okay, we could say that the cloudy white gel like precipitate completely dissolves. And then for iron, the dark orange fluffy precipitate did not dissolve. Okay. Then I see what you're doing. Okay, so okay. Now for aluminum, when we add HCl, we have the precipitate, cloudy wisps of precipitate. So it somewhat dissolves. Partially dissolves into cloudy wisps of precipitate. And for iron, didn't need to reattain. Well, they're not adding. Okay, since this is only if precipitate was present. It says that they're not adding anything to the iron. Didn't need to reattain precipitate. So what? Not applicable, I guess. All right.
So wait, with cobalt, I'm confused. They say no precipitate formed in the first one.
Yeah, I think these are happening separately.
Huh?
I think they're happening separately. Like first of all. Sorry. Okay. So all right, we first add the ammonia, and oh wait, JK. So it is adding it to the NaOH mixture.
Yeah.
So what were you asking about?
For cobalt, I'm like, because it says light peach added precipitate over here.
Yeah.
For table 2, and then table 3, it has another observation as well. But would that even be put in? Because they didn't even add any NaOH. Well, they did add NaOH to the cobalt, but then. It doesn't seem like they added it for HCl.
Yeah. So I think, yeah, we can see what if we need to change anything, we can see that afterwards. But I think what they're doing is like these different data tables are just added. So like, table 1 is when you add ammonia table 2 is when you add sodium hydroxide, but what we're doing in our experiment is we're adding the ammonia first, and then to that solution that has already had ammonia to it, we add the sodium hydroxide.
And we're adding the HCl.
Yes. So for our purposes,
seems like they're trying to titrate it.
What's up?
It almost seeming like they're trying to titrate it or neutralize it.
Yeah.
Because they had a light base and then they had a strong base, but then immediately followed with a strong acid.
Correct. Yeah. So our table so far makes sense. And our unknown is definitely going to be some mixture of aluminum and iron, I believe.
Okay.
Okay. So let's see. So okay. Analysis. So after you finish these tests on the known solutions, which is what we did, try to work out a series of experiments you can perform on the mixture. Okay. So on a mixture. Okay. So okay. Now, I guess we're starting on our unknown.
I guess.
So
I guess that would be it.
Would I write that in data or results?
In results, I guess, to find the unknown. Because
okay, I'm just gonna write it somewhere, and then we can figure out where we put it after.
Yeah, no, it's gonna be results, because right, state which unknown you analyze.
Okay, so
procedures you performed on your unknown.
So this is what we'll do. So I'll just write it, and we'll figure out where to put it later. So, unknown 6 was assigned. Unknown 6 was investigated, and okay, and the process. So unknown 6 was investigated in the following whatever method or something. Wait, it says, okay, state which unknown you've analyzed, what procedures you performed, results. Okay, so unknown 6 was analyzed using the following procedure. So I'll put down something like, what the hell? Okay, so first we added, NH3 was added to the unknown, and the results were indicated the presence of a clear colorless liquid on top and a rust-colored precipitate on the bottom. Then NaOH. Okay, so due to the existence of a precipitate, NaOH was added to the mixture, and the rust-colored precipitate did not dissolve and remained intact. Okay, then due to the existence of the aforementioned precipitate, HCl was added to the mixture and milky cloudy precipitate came back. Milky cloudy precipitate. So, okay. Clear colorless liquid on top. Okay, it was added to the mixture and a milky / cloudy precipitate formed. Okay, so basically what we are doing is cloudy white gel-like precipitate. So that means, you know, that's essentially what it turns back into with the the cloudy wisps of precipitate.
Mm-hmm.
So this.
Oh yeah, this can go into the experimental data. I mean the experimental on the top, if you see. Yeah, that's where procedures usually go. Okay.
Whoops.
You're good. You can keep writing. I was just letting you know that's where it goes.
Okay. Okay. All right, a detailed set of detailed set of procedures. Okay, so experiments you performed on the known solutions and their results. So okay, before that, I'll say the experiment. Okay, well, let's see. Wait, above. Okay. 4 cations were investigated, or rather, were analyzed using using a procedure that involved the addition of NH3, NH3, NaOH, that involved the addition of NH3 and observation of either changes in color of the solution or whether or not a precipitate forms in addition to the color of the precipitate. Only if a precipitate had formed is NaOH, is NaOH added to the previous mixture containing the known cations and the NH3, 3 added. To observe if there is a color change and or a precipitate forming or dissolving. After this, HCl is added to the previous mixture containing the known cation. I should say singular cation here. Containing the known cation, the NH3, the Na, and the NaOH, to observe if there is a color change and or a precipitate forming or dissolving. This systematic analysis enables the separation of, or rather, enables the separation of the 4 different cations, which leads to a sound qualitative procedure that will be used for our analysis of the unknown mixture. The results are in, let's call this table 1, which is basically known cation observations. So the results are in table 1. Okay. Then over here we can say the results for unknown 6 are in table 2. And then, okay, I see what you're doing. Okay, so we did the experiments for the known solutions and the results. A detailed set of, to analyze any unknown solution. Results of, so we did the results of the unknown. So we just have to do the one in the middle, the detailed set of procedures to analyze any unknown solution. So detailed enough so a student can follow your, okay, so we could do something like, okay, we could do something like this. Okay, so detailed set of procedures to use to analyze. Okay, so the analysis of any unknown solution containing, you know, either 1, 2, 3, or all 4 of the cations could be done in the following systematic manner, whatever. So basically, we can say that. Let's see. We could say. I wonder if I could how I can make like a logic kind of map kind of little thing. But let's see what I can do. Chart, drawing, table, like a flow chart thing. Let's see. Whoops. Okay, I'm going to draw a flow chart here, okay? What the hell? Alright, this is gonna look really good. Just give me a sec. Okay. Or rather,
Oh, you're right. Yeah, this would fall under results.
Oh, are you able to see what I'm doing?
Robin?
Are you able to see what I'm doing?
No. But, the
I'm
thing where I
making...
thought it was data, it's gonna be results. Because these are the results are in table 1, and then when I look, that sounds way more like results than data.
Mm-hmm.
So,
So I'm making a flow chart right here.
oh,
So,
okay.
yeah, so I'm going to make it really nice. Okay, so...
Yeah, what you wrote here in the experimental with the 4 cations and everything, this paragraph, this can go all the way in the introduction.
Okay.
I'll let you edit it really quick, because I wasn't sure what you were saying in like a couple of sentences here. I think we were just like fast typing.
Yeah, so let me draw...
Do the flow chart. Don't worry about it. I'll fix the other stuff up.
Yeah, here, check out this in the chat.
Oh, that's cool.
Mm-hmm.
Oh, you got back your computer?
Mm-hmm.
Nice.
Yep.
So you're able to get back most of that equipment?
Yeah. I'll tell you more about it. And
Yeah, later.
Yeah.
Later. Don't worry. Alright, the next one with the next lab with the acidic salt. Seems better. I'll leave here. drawing looks good.
Thank you. Whoops.
Alright, I see it here now. Hello?
Yeah.
Sorry.
I put it there, but I still have to do one last thing.
Okay. Oh, this is for like the results, right?
Yeah, I just have to do it for... Mofo. Okay. F. Okay, what do you think?
I think it looks good. Great, actually.
Thanks. I was trying to make it so I can make the colors, the initial colors different for copper and stuff. And for some reason I couldn't get the, whatever. I couldn't get the subscripts working for some reason. Okay, I think I can fix that. There we go.
When you mess up somewhere?
No, I'm just making it nicer.
Oh, okay. Well, someone commented on the live chat.
Hahaha. YouTube Guru 21, let's get it. Alright, so there's that. So in the following systematic manner, and then I'll call this flow chart 1. How to, because this is supposed to be like a detailed set of procedures used to analyze any unknown. Okay, so how to analyze any unknown solution. Okay. Oh, whoops. Okay.
Oh, there's an A inside the F.
Yeah, I fixed that.
Okay. Alright. That's actually perfect. That worked.
Okay.
That's a perfect experimental.
Mm-hmm.
That's thorough and everything. Okay, so we're finished with that. That's good. Oh, can we look at the introduction really quick?
Wait, where did that stuff about table 1 go?
Robin?
For experimental, the first thing we do is the experiments for the known. Oh, you put it in the introduction?
Yeah.
So that should be the first part of the experimental.
I know that it should.
Yep.
But the teacher would prefer it to be in the introduction. Like you're supposed to explain like what they're gonna do in words.
Yeah.
And stuff in the introduction, and then the steps are in the experimental. So like the flow chart and then the steps over here should be in the experimental, but then that paragraph with the 4 cations should be in the introduction.
Mm-hmm. Cause
yeah.
In the part that says your report, it says first in your report you should include the experiments you performed on the known solutions and their results. Then the detailed set of procedures that can be used to analyze any unknown. And the last thing, our analysis of the unknown.
Okay.
So if you could write it in the introduction, like in a less detailed way, that should be good.
Okay. So then we'll keep what you wrote. Okay.
So we could say
what you wrote.
So here I would write this, because I see it says in the first part of the experiment, you're doing it on whatever known, right?
Yeah.
And then using that, the results from that, and logical reasoning. So, okay, here, check this out. So let's see. And yeah, in the yesteryears, okay. So basically, first observations are made using known solutions of known cations of known cations. Observations are made using solutions of known cations to let's see. Using known Okay, so first solutions of known cations are tested in various circumstances to obtain results that indicate that no two cations behave in the same exact way. This is, I guess it's a control. This is the control that will be used to develop a logical, so this is the control that will be used to develop a logical, systematic procedure to ascertain the identity of the cation in any unknown solution. And lastly, this this method is used to determine the identity of an unknown solution that indicates proof of principle. Okay. So I may start with like experiment 1, known solutions and their results, and then
so that introduction works then. Okay.
Systematic. Okay. Known solutions and their results, and then methodology for obtaining determining identity of unknown solution. Maybe I should say, yeah, okay. Let's see.
Alright, perfect, that works.
And then I can write, okay. Application of methodology to unknown solution. Okay. Okay. Okay, how are we doing so far?
Ivan?
So how are we doing so far?
Yeah, no, this is perfect. The experimental is completely good. Yeah, this can be, what do you call it? Left as is. The introduction's perfect amount. So next is just to finish up the experiment. I mean, to finish up to get the results of what cations are in the solution. And then discuss them. There's another flowchart coming in there?
Yep.
So we can get a move on this, I guess. How would I find the cations then here?
So just basically whatever what I was writing in that thing, we're just gonna follow those steps.
Okay.
So, here.
Yeah, the steps that were inside the chart over here, and then you compare them to the chart where we had the no cation observations.
Mm-hmm.
Okay. Is another person in here?
Oh no, I just opened it up on another thing.
Oh.
Yeah.
I was like,
What? Is it blue? Did you make it blue or something?
11?
Alright, never mind. Okay, so let's see. Trying to see how best to do this. Let's see. Clear and rust-colored precipitate on the bottom. Okay, so maybe I could do something like to do like a separator kind of thing. Okay, wait. I'll do this kind of thing. Addition of NH3.
Alright, I'm gonna figure out this unknown while you do that.
Okay.
Figure out what cations are in this, and then once I figure that out, I'm gonna start writing the introduction for the next lab report I'll need help on.
Yes.
And stuff. So yeah. Because once I finish that, I guess I'll be finished next little chart, and then we can move on to discussion.
Mm-hmm.
Once I'm able to write that intro. And get the results tallied in. So let's see, clear colorless liquid on the top, rust colored liquid on the bottom. So that means that it's going to be aluminum and P3+. Precipitate did not dissolve. So and remain the precipitate. Okay. LP clouds. Precipitate turn. So cations found in this unknown 6. Aluminum 3+ and iron 3+. So we found 2 of the 4. All right, so all right, and so I found which cation it was.
Okay.
Which cations there's 2 that were found in there. That would make sense. All right, so I'm going to move on to the 6 volt. At least for the next one, we won't have to worry about making a flow chart. This one's just straight up finding and using molar mass and stuff. A little difficult, but should be okay.
Shit.
Was it able to be fixed up?
Hmm?
Were you able to fix it?
Yeah.
Yeah, I sent you the files for the next one.
Okay. I didn't write anything for discussion or conclusion yet.
Okay. I mean, for discussion, you can literally just put down for a discussion, honestly, and then I can do the conclusion abstract. Because once discussion is done, the conclusion abstract basically follow the same thing, so I'll just follow what you said.
Okay. And discussion was just basically talking about the experiment, the results, and how it makes sense and stuff?
Yeah, according to this, it's, what do you call it? the results to obtain, how you use your results to prove the presence or actions of each of the 4 cations. So basically, like, talk about the results and then I guess that.
Yeah, if you can send me like that thing that explains what to write in the discussion again.
Oh,
Or
okay.
maybe you sent it to me already, but I just want.
Yeah, don't worry.
Yeah. Okay.
I'll do it. Like, we only have like an hour and 10 minutes left, and I want to use it. I want to use it correctly.
Okay.
So if you just do the discussion, I'll be able to follow through with the abstract. In conclusion, with no issues, they basically follow the same data. I mean, the same. So let's see. How to write a live report? Yeah, I think that's it. Yeah. Okay. So I sent you that, and I'm sending you this now. So the guidelines.
Okay.
Here's guidelines. Sorry, this is not a subject, but there it is.
I got the acidic salt stuff. Okay,
Yeah,
I got it. Okay, blah blah blah. Okay, discussion. Reiterate your results. Okay. Oh yeah, sources of error and stuff. Okay.
Okay. That was a long ass introduction. For a relatively shorter explanation, I think. You did?
Yeah, I'm almost done with the conclusion here.
Oh, thanks. Okay, cool.
Okay. I think I am done.
Yeah, and then I'll write the abstract. Yeah. Yeah, like another 20 minutes hopping. Mm-hmm. And
Yeah.
can you come and take a look with the acidic salt stuff?
Okay.
Finish there.
All right. So what exactly do you need me to look at, or?
If you can open the what do you call it, little PDF I sent of identifying an acidic salt.
Okay.
And then there's the data, but all I need you to refer to is titration curve D, because I copied the data set that's correlated with my assigned number.
Wait, I'm sorry. What did you need?
The two things I sent you in the email
Yeah, I'm looking at
and
them.
stuff. One of them is the PDF of the PowerPoint that's used for the experiment, and then the other one's a data set.
Yeah.
And whatever, but disregard the numbers on that PDF. Just look at the thing that says titration curve D on the bottom. There's like 4 graphs on the right of it. Because the data I already have written.
Oh, titration curve B? Okay,
on the
yeah.
report.
Okay, what about it?
Yeah, D.
Oh, D?
Yeah, as in dog.
Okay, what about it?
No, I'm just saying, like, when what do you call it? It's kind of refer to it, or like what it's talking about in the experiment here to do. That's what it is. I'm just letting you know.
Okay.
Yeah, I'm just letting you know. Disregard it for now, but let's just.
Is there a
I'll
particular
open the PowerPoint.
data set that you're working with?
What happened?
Is there a particular data set that you're working with? That you're
That's on
assigned?
my report. If you scroll to the results.
Table 1. I see various compounds, I guess.
Okay.
Oh, data set 1?
First, no, the table 1 is just the possible acidic salts that can be found in the solution. So we'll just refer to that back at the end of the lab.
Correct.
It's again like finding the unknown, like the same thing we did last.
Yeah.
So table 2 though is the data set.
So the one that you were assigned?
Yeah.
Okay.
Is the one that was assigned.
So it seems like it's titration curve C, isn't it? Titration curve C?
Well, I was assigned D.
Wait.
I was assigned to use B.
Data set
PKA.
Data set 1 on the thing with the data set table.
Yeah. Oh, I'm sorry. Yeah. Sorry, it says C, but I'm 21.
Okay, so data set 21. Okay, I see your values. Okay, so yeah, it's supposed to look like titration curve D. Okay. So, okay, so what exactly do you need from
so
there?
if you look at the PowerPoint here.
Yep.
Okay, so on my screen.
Yeah.
You see it? Okay, so identifying acidic salt. So you see goals to determine what acidic salt is an unknown solution. So we'll need to know the molar mass of the acidic salt and the pKa. To find it.
Okay, so let's see. Okay, we have the molar masses and the pKa. So first of all, we have grams of KHP. Grams of KHP. The hell is that?
What do you call it? I think it's the
KH2PO4.
Huh?
What? The KHP.
What did you say?
Sorry. What's the KHP? Oh wait.
I'm not.
Is it? Oh, is that something that we don't know?
No. It says grams of KHP on the result here. If you look.
Yeah.
I guess that's just like what was inside the solution.
So we have to see which thing it is, like from these?
No, we're not finding KHP. I think it's just going to be used in calculations. and stuff, but we're finding the pKa and the molar mass. So you see how
I see what's going on.
You see?
Yeah.
Yeah.
So okay, so KHP is just a general term that we have to that could be any one of these salts then.
Possibly. I
yeah,
think that's what it probably means.
That's what it is basically.
Okay. So solution. All right. So what made salts acidic? I already wrote that down. We know why. Now we're using a titration, equivalence point, and endpoint for finding the equivalence.
So yeah. So basically, what we're going to start with is so okay, salt titration. Let's see, mass of salt. Let's see.
And standardizing it, procedure outline. So then this is like the calculations for part 1.
So okay, so basically, okay, let's see. Okay, so here I'll do something. Okay. Oh wait. I got it. Okay. So at the equivalence point, we have basically moles of base added is equal to moles of the acid in solution. So now I'm going to look at, let me take a closer look at this titration curve thing over here. Titration curve D. Okay, so seems like the equivalence point is like a little higher than 7, is it?
What, and D?
Yeah, and that titration curve?
Yeah, it's just a little above 7, so I would say like 7.15, something like that.
Got it. Okay. So that's basically when you have the moles of base added equal to the moles of the acid that you add. So
yeah.
So okay. So basically, all right. So let me see something. Wait. Okay. So. Okay, so okay, what do you here, I'll use like a calculator also. Let's see, 22.46 minus 3.02 is equal to 19.44. I'll merge these. I'll center it. Okay, volume of whatever. Yeah. Okay. So then let's see. Okay, moles of that.
Okay,
Yeah.
okay. Yeah, sorry. Got it.
Okay, so then moles of KHP is equal to, okay, so moles of, all right, okay, moles of KHP, which is going to be equal to the moles of NaOH. So we have the, wait, what's this over here? Wait, standardization. Hold on. NaOH.
Oh,
Like, does it tell you the concentration of the NaOH?
We're working, according to this, I believe we're working with the standardization of the NaOH first. Because it's two different parts to this.
Yeah, I just need to know the what is it called? The the concentration of NaOH. Oh wait, standardizing okay, so standardizing NaOH means we confirm the concentration. Okay, all right. Okay, moles of NaOH at equivalence point. Concentration is the moles of Okay, so we find the moles of NaOH at the moles of KHP are equal to. Okay, so moles of KHP is equal to moles NaOH at equivalence points. Okay, so basically they do the mass over the molar mass of it. So okay, let's see. Make a solution of KHP. What the hell are they talking about with that?
I wish I knew.
So, I mean, in the thing they're showing... Oh, wait. Okay, hold on. I think I know. KHP is what? Molecule. Oh, it's just potassium hydrogen phthalate. It's the same thing. It's the thing all the way on the bottom.
Okay.
The thing that's 204.23. Okay?
204.23? Where?
204.23 grams per mole.
Where?
It's in table 1, it's the bottom.
I see it. So that's KHP?
Yeah.
Oh. Why didn't they just say it like that?
So alright, now we do 1.6, alright, 1.621 divided by 204.23, and we get the moles, so that's equal to 0.0079 whatever 4.
Yeah, only 3 digits.
Yeah, and that's equal to whatever the moles of NaOH at the equivalence point. Correct. And so now we take so now we take whatever. Now let's see. Concentration of NaOH is that. So we basically divide it by, so concentration of NaOH. I don't know how to make, I'll fix this graph later, but I'll just make like, whatever. I'll insert another row. So basically NaOH concentration, that is just going to be our number, right, divided by 0.01944. Okay, so I get 0.4083. Whatever, molar, I guess. I guess it doesn't really matter. So okay, that's the concentration of NaOH, right? So that's that first thing that we needed to find. We needed to find and then the molar mass of the acidic salt. So wait, hold on. Molar mass of the acidic salt. We have the so let's see. So we do the titration thing. Okay. Okay, so all right, we have that. So then we find pKa, and then all right, so we find pKa before we find concentration of blah 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 salt.
Yeah.
So this is what we're going to do. So the pH. So okay. Okay, all right. pH at which half, at the half equivalence point, the pH is equal to the pKa. So let's look for that. That's basically, the half equivalence point is like the midpoint of that that titration curve's like flat region.
Mm-hmm.
And it seems like the midpoint is like what? Like maybe like a pH of like 5.5 perhaps?
I guess.
Oh wait, no, it has to be, wait, my bad. So
Wait, what are you asking?
pH is equal to pKa, so it'll be 5.41.
Yeah.
Exactly. So 5.41 is that's the
pKa of the KHP.
Yeah, that's the pKa. And we put that into the Henderson-Hasselbalch thing. So let's see. So okay, so here we go. So okay, equivalent, all of it has been neutralized. Okay, half. Okay, so weak. Hold on. Equivalence point. I see. Okay, I see what we're doing. So we do the KHP thing first to find the stuff for NaOH, and then we do it with some unknown salt, and then we figure it out. So okay, so basically, let's see. So the concentration of, okay, it's that. All right. So half of it has been neutralized, is there. Equivalence point, all of it. And the other thing is half of it. So half equivalence point, and then equivalence point is like 7. Okay, so all right, so let me see. So pH is equal to pKa, which is equal to pKa is equal to 5.41. Now, that's at the half equivalence point, and then at the equivalence point, all of it has been neutralized. So I see. So it's half of the volume. Okay. So okay. The half equivalence point is half of the volume. So double the volume will be at the equivalence point. So basically, all right, let's see. pH is equal to pKa is equal to 5.41 at the half equivalence point, which means half of the acid KHP has been neutralized. This occurs at half of the volume of NaOH added. Okay, so which is just 19.44 milliliters. So at the equivalence point, we have double the volume of NaOH added, which is, let's put this in 19.44 times 2, which is 38.88 milliliters. Got it. So now, now finding the molar mass of the salt at the equivalence point, the moles of the acidic salt is equal. Alright, well, I know that. Moles of that, okay. Moles of that, okay. So let's see. Okay, so now we're going to deal with our unknown and the volume of that. So 11 point, wait, titration. Okay, so the volume, so 11.99 mLs. I'm just trying to see if it's, all right, let me see. For our unknown thing, let me see this thing again. Okay, titrate, okay, make solution, adding the unknown salt, some water, titrate using standardized NaOH. So we have, okay, got it, okay. Okay, got it, okay, so this is what we'll do. So, okay, when adding the unknown salt with 11.99 milliliters of 0.4083 molar NaOH, the amount of, okay, let me do that, so 0.4083 times 0.01199 is equal to, okay, producing 0.00489, 9 moles of NaOH. Okay, that's how many moles of NaOH we have. And this should be equivalent. What's that?
I think we're out of time.
Oh, okay. So what do you want to do?
Oh.
I think we're almost done. I think we could finish in like 4 minutes. Let me see. So this should be equivalent to the amount of moles of the unknown acidic salt. So the moles of acidic salt would be 1 gram divided by 0.0049 moles of acidic salt divided by 1 gram of acidic salt, which is equal to 0.0049 grams per mole. That's the molar mass of the salt.
Okay. So the molar mass of the salt is 0.0049?
0.0049?
Yeah.
I believe so. Well, wait, that doesn't make sense. What am I talking about? What am I doing? Let's see. Oh, crap, I did it the other way around. My bad. So, it's the other way around. So it's 1 over 1 gram divided of acidic salt divided by 0.00049 moles of acidic salt. So 1 divided by 0.0049 gives us, gives us 204.08 grams per mole. That is that just freaking
KHP.
Okay.
KHP.
Okay. Hopefully I did that right.
Oh.
Oh yeah, no, it is right because the pH is equal to pKa. But I mean, yeah, that's what I did if I did everything right. So that's what you should get.
The titration.
Yeah.
The titration curve reads 7.15 when the pKa of the acidic ion is 5.41 for KHP.
Wait. Sorry, say that again.
The titration curve over here that we're following.
Yeah.
Which is the number I put down.
Yeah.
That's the pH of it. That's the pKa.
Oh yeah. So that's when you'd use the Henderson-Hasselbalch equation.
Oh, and that's what you just used?
Yeah. So it would be plus log of the concentration that we had for the weak acid, which is the what is it? It's the that many moles. What's whatever the volume is that we use? Unknown salt into some water. I don't know how much of it. Oh, it'll probably be in that thing. Let's see.
So if pH equals pKa, right, and the pKa equals 5.41, over here at half the equivalence point. What do we do with the 7.151?
No, so okay, that's not, so here, check it out. So pH is equal to 7.15 or something is equal to 5.41 plus the log of the whatever, the conjugate base to the
base and the weak acid. Okay.
The
moles of it.
Concentrations.
Yeah, the concentrations of both.
Yes. So basically,
both of them are 0.0049.
So you use that when oh wait.
Sorry, I just wasn't getting it over
Mm-hmm.
here. Because the teacher over here went straight off the graph.
Yeah.
Like her thing read 9.35 basically. And then that's what she used to find the pK of the acidic ion on the table.
Mm-hmm.
Which the closest is NH4Cl. But we get we get 7.15, but we get 204.08.
So okay, when we're adding, volume of NaOH. So they're saying, okay. Let's see. We are that much to titrate the unknown, which is made by that and water. Find the molar mass. Okay, so that's what we did. So went unknown salt with 11.99 of that. Wait, do they add each of these? I wonder. So no, they don't. Wait, do they?
They're not supposed to.
Okay, whatever. So that's producing that many moles of any equivalent to the amount of moles of the unknown acidic salt. The unknown acidic salt. The amount 1 gram is equal to that many moles of acidic salt. You should basically get some number that is going to give you like the difference between 7.15 and 5.41.
Mm-hmm.
So, like, so I'll just do that. So 7.15 minus 5.41 gives us 1.74. Let's take the anti-log of that. Where is that? Where's the freaking anti-log on this? What the hell?
So you got 1.74?
Yeah, I need the... Well, I guess the anti-log is just 10 to it. So 54.95 is the ratio of conjugate base to the weak acid.
Okay. Well, if you get 1.74 for your pKa.
Oh no, that's what you get for that log value.
Okay.
So in other words, I'd put down freaking weak acid, 1 gram, that many moles. Anyway, this basically, like, when you do the I'll just write whatever, conjugate base over the weak acid. Okay, that is what you get. That's where you get the 7.15 from. The 5.41 is the pKa.
Oh.
Yeah.
I got it. Got it. Okay. So that makes way more sense. So then our molar mass of the acidic salt is what?
204.08.
Okay. That's not really close to 5.41 though.
No. So we're trying to find just the So here, let me do one last thing. So we got.
Actually, wait. I might have been reading this wrong. Where's the equivalence point? equivalence point is supposed to be right before it strays, right? Right before it keeps going, so right where it stops. So it stops over here at like 6.15 or something. I'm not even sure.
So okay, we got 0.00. Okay, so 0.0049 moles of the acidic salt divided by I wish it said. Okay, so I guess equivalence point moles of that is equal to moles of that concentrate. Okay, well, okay. So okay, so okay, this. Okay, concentration of that times that. Wait. I don't even know if we need to know that. I think we got everything that they want.
Okay.
Like we have, but yeah, just that this isn't the pKa. That's just the pH after you do the Henderson-Hasselbalch equation.
Mm-hmm.
So the 1.7.
Oh, okay.
Yeah, the 1.74 is just the log of the concentration of the conjugate base to the concentration of the weak acid, basically.
Okay. So then the results are finished.
Yeah, pretty much.
Okay. So what I write in the discussion?
Oh, you know what? I didn't notice before that it tells wait, it doesn't tell us. Never mind. But okay, sorry. What were you asking?
What would I put in the discussion?
Just like thing that you sent me. Just how to write a lab report.
Mm-hmm.
Reiterate your results, possible sources of error.
Okay, so the results of the experiment were the 5.41 pH.
Mm-hmm.
And then the 204.08 grams per mole.
Mm-hmm.
And which led us to our acidic salt being KHP.
Yeah, pretty much.
Okay, so it shouldn't be a really long discussion. Okay, and then the graph. How do I fix this?
Let's see. Initial, final. This is just whatever the total. This is the moles of that crap at equivalence point. Oh, you know what? I think that makes sense. 0.00794 divided by 0.0049. Okay, that makes sense then. But anyway, so okay, fixing the graph. You could just let's see. We could just let's see that let's do this. Let's do what is it? Volume of NaOH added. Oh wait, crap.
Oh yeah, it would probably be easier to put it that way. Okay, makes sense. So you can just get rid of those cells, those columns, I mean the rows. Right? That's what you're doing? Awesome. Okay.
Did I delete too much?
Pardon?
Okay.
Oh, did you need the prior number?
Oh no, I thought I deleted too much, but okay.
So you put 19.44.
Alright. Like, yeah, all you need to find is basically, you know, whatever. The,
Okay.
you know, the, molar mass and the pKa. So, you know, we got the pKa here, 5.41. Got the molar mass here. So,
yeah.
In other words, we determined that it was a Ka treat.
Alright, perfect. And then I can just do the conclusions and abstract. That'll be easy then.
Yep.
Alright. Shouldn't be a very long discussion then.
Mm-hmm. Alright.
I'll just make up 2 sentences of error.
Okay.
So, alright, sounds good.
Alright.
Thanks. Hope stuff keeps going okay.
Yep. Thank you.
No problem.
Alright. So,
Alright, so
I'll send you the Zell stuff. Or if you can send me the Zell stuff, I'll do a request.
yeah, you, what do you call it? Send me the